That's right. Oh my goodness. Yeah, next fall I'll be back. You know where to find me. Oh yeah. It's a great friend.
Do you like your new home?
You know, I'm slow to change there when Did you get more room, less room? More, yeah. You remember kind of squeezing into the back of that little shoebox at the classroom where you used to rolling out. So it is a more comfortable room.
You know what that means? They'll cut your wages.
You wanted me, so they come. I know, you're the guy that told me it was coming.
I got it. there, Lucky.
I think it is. I think it is.
Absolutely. Good maniac, I gotta be.
Shows you what happens when you show up late.
No, I didn't know him until I got here. Then one day he said, "Where are you from?" I said, "I'm retired from Maine." Maine, whereabouts in Maine? I said, "I was shooting down in Buckfield." He said, "Buckfield? That's right next to Liverpool." I said, "Right." He said, "I'm from Liverpool."
Done stuff.
Never saw it. It's nice enough. But when she should from there to here, much more expensive here. If I had a piece of property here, the size I have in the house that I have, I'd have at least $500,000. We bought a little house, a little piece of property.
We came, Alexander, Virginia. Said it land was a lot more expensive there.
Than here. Of course, we have to Washington State across the road.
And they don't stay there.
No, they don't. And every time they move out, somebody with more money moves in. And they all expect to get more than they my daughter went to Duke.
All right, everyone.
We could drive through that area and just see.
Well, welcome to the Kittitas County Historical Museum. My name is Sadie Thayer, and I am the director here. And it's my pleasure to introduce the first in our lecture series for the entire year. We're very fortunate that we have this lecture series, which is sponsored through our generous memberships and donations to the museum, and through support through organizations like Humanities Washington, which makes up a good number of our other lectures in the series. But tonight we are fortunately in the presence of a man who really needs no introduction. For many of you who've gone to his other lectures here at the museum or at Hal Holmes or a number of other locations in the community, Nick Zentner is known for his geological presentations. But those of you who are not familiar with him, he's done geology for years and years, teaching up at Central since 1992, where he teaches Geology 101, an intro class that's open to the public, as well as his Geological 351 Pacific Northwest Geology. And Nick has won a number of prestigious awards, as well as been featured on PBS, among a number of other publications and presentations, television and otherwise. So join me in welcoming Nick Zentner.
Well, everybody, it's great to see you. Boy, we ran out of chairs, I guess. Does anybody have an empty chair? You got one empty? Can we put the lights back on for just a second, please? So we got one empty chair there. Is this empty? No, you're holding it for somebody. You know, you should make yourself comfortable if possible. I mean, especially if you can't see the text that's on this screen. Let me give you another little test here. So, I mean, that's tough reading from the back of the room. So if you want to come up, sitting on the floor is maybe not great, but you're welcome to come up. and just kind of fill in some of these places, or right in here. I just feel like I should accommodate you somehow. Otherwise, I guess I don't know how much else I can do that way. So I want to thank you for coming tonight. I do have a new lecture that I've only given once before. It was about a month ago that I tried this. And that first crack at it is on the internet. It's on YouTube now, and so I'll make sure you know how to find it. In fact, I might as well tell you about that now, just in case you're interested. So, in case this really intrigues you, and there's a chance it will intrigue you, and a chance it will bore you, and you can't wait for this to be done. But just in case it intrigues you, this is my name, and this is my name.com. So, I've decided that I should find a place where all of my materials are in one place so people can find them. So if you go to nickzentner.com, you can find a lecture called Exotic Terranes of the Pacific Northwest. It's got a different title than tonight's talk. Tonight's talk is titled, what did I call it? Is Mount Stuart from Mexico? That's what I decided. Right? Cutting right to the point, right? I guess it worked. You're here. You want an answer to that question. But you won't find that title online. Again, you'll go to nickzentner.com and you'll find something called Exotic Terranes of the Pacific Northwest. I'll bet you'll find it. And much of what I have tonight for you is coming from that lecture. So, that was a programming note. Let's actually start with a very quick story, and then we'll get right into this content. You heard Sadie's introduction. I've been here a while now. 1992 is when I showed up, and I tell my students, 1992, that was before the internet. That was before email. That was before you could easily look up things, you know? Back in 92, most of us remember that. Well, we had to hike up to the 3rd floor of the university library or the library next door and find a book, and just that time wasting of trying to find your information going through these things, right? Well, I'm telling you that in part of this little story because some of you know a guy named Jack Powell, who was a geologist here in the valley for a long time. He's now a snowbird, and he's down south every winter, but he's still part of this valley. And I took over for Jack Powell in 1992 at the university. And so I rolled into town. I was newly married. We had our first child, a little baby. And our first couple days we're in town. We're just looking for a place to live. There were no apartments. It was mid-August, and we're trying to find some place to live. And we happened to be in Sandy Walker's office, real estate office, and she just got a phone in the middle of our meeting, and somebody had, given up on some reservation or something. She said, I got a duplex for you. It's right on the edge of campus. It's just off of 14th and Alder. So that's where we lived, in a little duplex. The point for that is, we were so focused on finding this apartment, we never looked to the north of this valley, this new home that we were going to be in. And we finally, the next day, took a little walk, and I got up on Craig's Hill, found Craig's Hill, went up there and looked to the north. I couldn't believe my eyes. This beautiful Teton-like skyline was going to be right there in this new town of ours, Ellensburg, Washington. The Stuarts, of course, and Mount Stuart. I could not believe it, especially since we totally missed it for the first 24 hours of being in the valley. So, to finish the story, I met Jack Powell. He helped me kind of get established here and learn a few basic things. And we were looking at Stuart on a little field trip. We're looking at that mountain range, and he says, can you believe a mountain like that is so beautiful and yet so controversial? And I said, I probably paused for a little while, and I said, I have no idea what you're talking about. Controversial? He says, well, yeah, Baja, BC, that's a big controversy. And again, I'm like, Baja, BC, I have no idea what you're talking about. And I couldn't get on my smartphone. I couldn't go on home and on my laptop and look this up. So it took me a while to figure out what he was talking about. And here we are, almost 30 years later, and I'm sharing with you something called Baja, BC. So it's an old idea that now is gaining steam in the scientific community. And I promise I've got slides, I've got images, I've got maps, but I want to do something here. Let's see if this works. I'm going to ask one more. This is high maintenance now. Can we turn the lights on one more time? And I want to do something with this portable whiteboard here. We'll see if this works, and if it doesn't, we'll just give up. Yeah, all of them. Yeah, great. Okay. So,
I'm going to try. So, I want, before we look at the maps, which are kind of complicated, I want to try to convey at least the message of this thing called Baja, BC. So I'm going to walk around the room. We'll see if this works. So this is my portable little chalkboard, whiteboard, and I've got a map of Canada and the U.S. and of Mexico. And I've got a red X for Mount Stuart. And I'm going to put two more X's on here. I'm going to put an X for the San Juan Islands, and I'm going to put an X for the bedrock between Wenatchee and Chelan. So far this is an underwhelming map. All I got is a lot of white places, and I got three little tiny little red X's up in Washington State. Okay, here's the controversy.
You can put it down when you're done.
Oh, I see what you did there. Thank you. Is this some sort of bomb? What is this? All right.
Better be a good lecture.
Yes. Here's the controversy that has existed for 50 years and still is a controversy today. Mount Stuart, San Juan Islands, bedrock between Wenatchee and Chelan. Did that rock originally form here in the Northwest, or did all of that rock form down here, down in Mexico? Did a part of Baja, Mexico get moved north 2,000 miles to what is now British Columbia? Do you get it now? Baja, BC? You take a piece of Mexico and move it north 2,000 miles so that it ends up in British Columbia. And you're like, well, Mount Stuart's not in British Columbia. Well, let me add to my sketch now. So now I'm going to make a big old block. And I think I'm going to give up on this in just a second because I've got better maps that you can see. But now I've got an actual red rectangle. I'll get to you in the front in just a second. So if we move this block from Baja, Mexico, up to British Columbia, Mount Stuart is on the trailing edge of that block. In other words, we're going to move this big block of crust from Mexico north, and the leading edge of that block is going to end up in British Columbia and damn near Alaska. But the trailing edge, the southern edge of that block, is us. So Stuart is right on the southern edge of this block. So let's just pause and realize what I'm trying to say here. There are more and more geologists recently, with this new evidence that I'm going to share with you tonight, that realize that everything from Ellensburg to the border, all of the North Cascades, was not created here. It was created in Mexico and was moved 2,000 miles. And I'm sure that you've got questions. How is that possible? When did this happen? Is it still happening today? Why in the hell would you believe that at all? Is there any evidence for that? Well, of course there has to be a bunch of evidence, otherwise I wouldn't waste your time with it. And before I get into it, I want to make sure you realize this is still a debatable topic. And I put this stuff on the internet, which I mentioned, and I'm sure I'm going to get some flack from some geologists who say, I can't believe you're sharing this Baja, BC thing. It's a bunch of baloney. But I went to a conference last fall in Seattle. It was a national conference, and there's a bunch of younger workers who have new techniques now that have bolstered this idea. And I'm officially excited about it. Okay? So, that's the end of the underwhelming whiteboard introduction to this lecture. And now I'm going to gently lift the ticking time bomb, the Betsy Johnson.
You can use it again if you need it.
Oh, thank you. All right, great. And the lights are off. Thank you very much for that. Okay, well, let's get right into this. So I'd like to start with the San Andreas Fault in California. That's an odd place to go, but you'll see why in just a second. Then I'd like to go to something called the Straight Creek Fault, which is here in Washington. Maybe you haven't heard about it. I'm guessing you have not heard about it. There's a reason you haven't. Then I'd like to do something called Assembling Washington, and then we'll finish with the From Mexico question mark. Okay, so let's start on a terrible morning in downtown San Francisco. 1906, Wednesday, April 18th. At 5:15 in the morning, there was a magnitude 7.9 earthquake. Have you heard about this great San Francisco earthquake? Almost all of downtown San Francisco was destroyed, mostly by fires after that earthquake. Has it ever dawned on you, if you walk around downtown San Francisco, there are no old buildings. There are no 19th century buildings because of this earthquake. Well, here are some guys the day after, homeless, downtown. They're better dressed than you and I put together, even though they're out of house and home. And that morning, a large section of the San Andreas Fault ruptured from Santa Cruz all the way up to Cape Mendocino, moved. And so what does that really mean? Well, the San Andreas Fault, as many of you know, is a strike-slip fault. So when there's an earthquake in California on this San Andreas Fault, the west side of the fault suddenly shifts north. Suddenly shifts north. We're doing a lot of shifting north today. We just did it on the whiteboard, right? How many miles we got to move our Baja BC thing? 2,000. Oh yes, you were listening. Yeah, good. 2,000 miles. Now this is not 2,000 miles of motion. In fact, that was a huge earthquake, the San Francisco earthquake, and this is a famous photograph. This is a fence. Of course, the fence was not built like this. The San Andreas Fault is right through this pasture, and that earthquake broke this fence cleanly and shifted it laterally by 10 feet. The ground did not open up. It's just a clean shift. So let's use this number. If you have a big earthquake on a section of the San Andreas Fault, you're going to shift the left side of the fault, or the west side of the fault, 10 feet in one earthquake. You're like, well, we got to go 2,000 miles. Well, if we got thousands and thousands and thousands of earthquakes over millions and millions and millions of years, we can do something like this. We can move something 2,000 miles. All right. So please realize what I'm saying. The San Andreas Fault is not moving things 2,000 miles. It's just a portion of the San Andreas Fault that ruptures 10 feet at a time. We do have a way, however, to realize the total offset on the San Andreas Fault. What I mean by that is, if we just look at earthquakes that have happened on this fault, can we figure out what's the total amount of shifting of the crust on this side versus this side? So this is Los Angeles and Santa Cruz. Here's San Francisco and Barstow, and here's the Salton Sea. And everything on this piece of California is moving in a different direction than this side. You've all heard about California falling into the ocean. Well, that's an urban myth that will not... I got 20-year-olds telling me that. It won't die. But that idea came from maps like this that showed up in newspapers in the 1970s, and people said, oh my God, there's this huge crack, this is probably going to fall in. That's not possible. But this is a piece of California that is moving to the north. And total offset-wise, we can go to the southern Sierra Nevada mountains and find some distinctive Mesozoic aged bedrock, and we can find that same distinctive Mesozoic aged bedrock over here on the other side of the fault. In other words, this is a way to measure or mark how much we've totally moved the crust since the age of the dinosaurs. And the answer is 200 miles. So there's been 200 miles of total movement of this rock along the San Andreas Fault in the last 30 million years. Now, I'm not testing you on this. You don't have to write this down. But those are some important numbers. One more time. Over 30 million years, we've had 200 miles of offset. Now, don't get too excited, please. This fault is not going to help us get Mexico up to British Columbia because it's too young. I think what I should have done and what I want to do right now, we don't need the bomb again, but this sketch has a very specific time window. In other words, moving Mexico to British Columbia is not happening anymore. You ready? Here's another little set of numbers. 75 to 45 million years ago. So moving Mount Stuart, if you buy this Baja BC thing and you're willing to at least contemplate this idea, we're doing our northern movement from Baja to British Columbia between 75 and 45 million years ago. Once we get to 45 million years ago, everything's here. Mount Stuart hasn't moved a lick in 45 million years. The rock of Mount Stuart is 93 million years. So in other words, we're making Mexican rock, We're making Stuart. We're making the rock of the San Juans. We're making the rock north of Wenatchee. I'll show you photos. That stuff's all older than 75 to 45. One more time. Are moving north 75 million to 45 million years ago. And this San Andreas Fault started 30 million years ago. It's too young. So in other words, it's a more modern version of what we think existed during the Baja BC time. Hey, I appreciate there's good energy in the room now. We've all settled down and settled into this. This is looking into the future just for fun. If we take Southern California, the stuff that's moving in a different direction, and we go into the future by 40 or 50 million years, we're going to have Baja, Mexico, and Los Angeles offshore of Vancouver. You know, it's going to be out here. Again, if we do this, you know, a couple inches a year, we do our 10 feet every time we have a big earthquake. So this is kind of a different way to look at Baja BC, but it's not really our topic tonight. Okay, now let's take what we just learned about the San Andreas Fault in California and realize Washington has its own version of the San Andreas Fault, and it's called the Straight Creek Fault. And you're like, well, I've never heard of the Straight Creek Fault, and should I be concerned? I mean, fault I haven't heard about. I got good news. The Straight Creek Fault has been dead for 35 million years. So let's talk about where this fault is and what the evidence we have for it. So here's a map of Washington. Here's Cle Elum. Here's I-90 going over Snoqualmie Pass. And if you look at geologic maps of old bedrock, you'll see a clean break. A clean break. That's the Straight Creek Fault. So what do I mean? Well, I've got some green rocks here on the other side of the Straight Creek Fault, and I've got some pink ones as well. And even from the back of the room, I assume you can see pink and green is here. And there's that same pink and green on the other side of the fault, but it's about 100 miles north of where it should be. So there, remember with the San Andreas, we had that 200 miles of offset? Here, on the Straight Creek Fault, we've had 100 miles of offset. So you're like, well, where is this thing? Well, every time I drive on I-90 and I see Easton, and I'm about to go up Easton Hill, and I got Lake Kittitas near me, that's where the Straight Creek Fault is coming right through Washington. So basically, Easton is where we have the fault. And what I am saying is, and I'll show you a couple maps here in just a second, everything on the west side of this fault has shifted north by 100 miles. That's not controversial. Even the most staunch opponents of Baja BC are fine with this message. So if you don't bite off and chew anything else I've got tonight, at least we can, I'm going to go back and forth here. This is fun. Okay? Doink, 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 doink. Okay? So I've got, so by 35 million years ago, we have all this motion. So again, I'm showing you two faults now that are not doing the job that we need. What's the job we need? We need to get Mount Stuart from Cabo San Lucas, essentially, up to just north of Ellensburg. This fault isn't going to work either. But my point is, there are two faults. They've got the wrong dates, but they've got the right kind of northern motion that has been happening in the American West. And before we go much further, I got to tell you, the main opponents to Baja BC say, I don't see the fault. Are you moving Mount Stuart 2,000 miles? Show me where the fault is. And I will show you why that's not possible. There's been so much geologic action since that time that it's buried. So, let's continue to work on that as we go. But realizing that we had rock that used to be next door to each other, I'm picking Cle Elum and Burlington. Can you picture Burlington on I-5? We're up by Mount Vernon on our way to Bellingham. So on this restored map of getting this bedrock back to where it used to be, essentially Cle Elum and Burlington were suburbs of each other before we start the earthquakes and the shifting on the Straight Creek Fault. So before we look at the details of that, here's why this is a challenge for us tonight. This is a map of the Pacific Northwest. This is brown lava, the Columbia basalt lava is like over by Vantage. That's stuff that is in our way tonight. We want to look at old rocks tonight, and this stuff's burying our stuff. burying our fault that we're looking for instance. But these yellow circles are places that we can look directly at some of these rocks that were not only shifted north, but also part of an exotic terrain story. So back to the Straight Creek Fault. Let's do it again because it's fun. Oh, this is kind of clever. So two of our boys went to Western. I know they grew up here, but they went to Western in Bellingham. And when we go visit them, it took 3 hours to drive to Bellingham. If they only had gone to school back then, it would have been a much shorter drive. Seattle, look, is to the southwest of us, actually. Thank you for laughing. Okay, great. So in case you're keeping detailed notes, the Straight Creek Fault was active between 50 and 35 and has been dead since 35 million years ago. So that's 15 million years of earthquake, totaling 100 miles of offset. Okay, finally, you'd think we'd start the lecture with this, right? This is the star of the show tonight. This is the Stuart Range. And many of you have spent much of your life exploring that range and hiking up to Ingalls Lake, etc. This is a beautiful image from Tammy Walton that she gave me permission to use for this lecture. And this is just this past fall. My knees were feeling good that day, and my wife and I hiked up to Earl Peak. So many of us know that in the upper Teanaway we kind of have these orange and kind of greenish, grungy looking rocks, and then Stuart is very different. Stuart is granite. So I'd like to look at these two rocks now with this new set of eyes, going, oh, that's beautiful, that looks like home. But geologically, is this home? It's not. This is, if you're taking my bait here, this is Mexican crust. You can stamp Mexico right on that. Does that deeply offend you? Maybe it does. Actually, had a few people come up after that lecture a month ago. They were not happy. Complete Mexico. I didn't anticipate that. All right, so this is my wife who teaches at the high school, and she's in much better shape than I am. But we stopped, and I knew I was working on this lecture, so we took a bunch of photos. So some of you know this green rock of the upper Teanaway. And that's a key part of our story here. It's serpentinite. And serpentinite is a metamorphic rock that forms only in the oceans. So maybe that's, if we're just looking for things we can hang our hat on and tell somebody tomorrow you went to the talk down at the museum and what did you learn? Maybe some of these numbers aren't going to work, but maybe you can remember. Green rock in the Teanaway, oceans, for sure. And we know that because we've dredged the ocean floors, and we've explored these places where one tectonic plate dives beneath another, and we found these places called subduction complexes, where we're scraping off a bunch of ocean rock and adding it to the other plate. This is where serpentinite is formed. These map makers chose green for a reason. The green rocks are coming from that particular spot. So another lecture sometime will be trying to address how you're going to take rock from here. We're way below sea level, aren't we? How are we going to get it out of the ocean and get it 9,000 feet above sea level, which is the case of Mount Shuckson, or 6,000 feet above sea level, which is in Earl Peak country? You need a lot of time. You need a lot of tectonic activity, and that's not our focus tonight. But here's hiking on the trail up to Ingalls Ridge and Ingalls Lake, and many of you know that the rocks are either orange or green. Why is that? Well, this is a green rock also that just happens to weather to orange. The chemistry of this serpentinite is unusual. Plants hate serpentinite. There's hardly any vegetation growing when there's serpentinite. So it's this green, waxy, metamorphic rock from the oceans that weathers to this deep orange. This is not an altered colored slide. This is what it really looks like if you've been hiking up Gallagher Head and places like that. And if we get up to Ingalls Lake and beautiful Mount Stuart behind us, this is the serpentinite. 93-million-year-old granite of Mount Stuart, 150-million-year-old serpentinite of the upper Teanaway, Mexico. Mexico. Artsy shot. Now, are there other places we can find that same green, metamorphic, oceanic rock? You bet. Here's Bellingham and I-5. Here's Mount Baker, an active volcano. That's not serpentinite. A few of you might know Mount Shuksan. Beautiful mountain, nothing but green schist, which is a cousin of serpentinite. Same idea. Metamorphic, ocean crust, subduction complex. And so when you climb and hike up to the top of Mount Shuksan, you're going up through this green oceanic rock, just like we have in the upper Tianoi. Mexico. So we really have two challenges tonight, maybe more than two, but our two main challenges are, much of this rock in the North Cascades is from the oceans, and then once we get it out of the oceans, we're sending it north. So it's kind of a 1-2 punch, which is a complicated set of ideas. Hopefully you're up to the challenge. Green, ocean, green, schist. She's at 9127, more than 9,000 feet above sea level. She's standing on top of Mount Shuksan, which is made out of ocean rock. Amazing. Here's a cartoon of Washington. So here's Spokane over here. This is a cross-section, underground view. Of course, here are the Cascades. So I-90 is going to get us to Ellensburg and up and over the pass and Seattle and then out to ocean shores. But again, if we can get underneath all these lavas, we don't care about the Cascades tonight or the Columbia River basalts. We care about these basement rocks of Washington. And notice that half of Washington is this green accreted terrain material, these exotic terranes, or this stuff that came in off of the ocean. Again, it's not only here, but it's been sliced and diced by one of our friends, the Straight Creek Fault. Let's go back to that and talk about specifically where we can find more of that green rock, and then we'll get into the Mexico evidence. So here's Easton. Here's, I think I said Kittitas, I meant Kittitas, and the Cle Elum Lake. So there's a spot on French Cabin Creek that's basically the ridge between Cle Elum Lake and Kittitas. And I went up there in early November and found some beautiful, I got a tip on where this was, and there's some beautiful green metamorphic rock. Again, more of this green schist that's beautifully swirled. I don't know how well you can see that, but this is a gorgeous metamorphic rock that tells us of this old ocean story. And then if we abruptly leave the Cle Elum area, and remember, cross the fault and go 100 miles north, we can get up to the Burlington area. And here's I-5 in the distance heading to Bellingham, and here's Burlington Hill, which is just north of downtown Burlington. Same green rock. They're cousins of each other. They're suburbs of each other that are now offset by 100 miles. Okay, I think we've hit that pretty hard. I think we're moving on. I've decided we're moving on. Oh, but this is, I gotta stop here. So here's Seattle and the Strait of Juan de Fuca, Vancouver Island, Olympic Peninsula. Look at all this wonderful geology of the Olympic Peninsula, which is essentially material that's been scraped off of the ocean and been added gradually to the edge of Washington. So there's a long history of this, and there's also a history, a recent history. This is still happening as the Olympic Peninsula continues to accumulate material. Now, you need to realize, and I guess I didn't realize until this past winter when I put this lecture together, to totally understand all of these ocean rocks in Washington, we need to expand our view from Alaska down to Mexico. This is an entire North America story. So if we go down to San Francisco again briefly, and we look at what the Golden Gate Bridge is anchored in, it's that same serpentinite. So this is an entire west coast of North America story. This is a North America story tonight, even though Mount Stuart was at the centerpiece of this controversy 50 million years ago. From the family archives, this is my first trip out west with my family. Okay, so we're done with the ocean stuff. We're done with that. We already looked at that. Done. Oh, I do want to go to the San Juan Islands very quickly. Many of us love the San Juan Islands, and they are part of this adding material from the ocean story. Of course, the geology is different over there. We've got to fight through all this biology to get to the rocks. It's much more difficult. But if we get up on Fidalgo Island and we look south, we realize that these rocks also have an oceanic story, also are part of Mexico originally. I don't know if you're feeling better or worse about that as I keep repeating it. Deception Pass, we're going to film a new little PBS episode there this summer. We're excited about that. Ribbon Chert is actually from the ocean floor itself, not one of these subduction complexes, but truly out in the Pacific someplace. And this is at Rosario Head, just north of Deception Pass. I came to hear about Mount Stuart. What's this guy doing? He's all over the place. Mount Stuart is just a tip of this major iceberg that we're talking about. This is a Western North America story, and Mount Stuart, that's the beauty of this. Our local landmark is part of a regional discussion. And by regional, I mean much of our Western continent. Okay, so let's zero in now on this Mexico thing. Some of you may remember that in 2012, not that long ago, the first dinosaur bone in Washington was found. Does anybody remember this? In the San Juan Islands, there's one tiny little island called Sucia Island, and it has a certain kind of sedimentary rock that's of the right age. It's 80 million years old. These guys were up from the Burke Museum from the University of Washington. They were looking for ammonites, a totally different kind of fossil. But they found a portion of a thigh bone from a Tyrannosaurus rex. A portion of a dinosaur bone from a Tyrannosaurus rex in Washington State. The first one ever found. The first dinosaur bone ever found. And you're like, well, I'm confused by that. I see dinosaur statues when I go over to Vantage. I see dinosaur statues when I go down to Granger. And it is confusing as hell, but there are no dinosaurs there. That's them trying to get you off of the freeway. All right. So there we go. Questions, all the phone calls, emails. Well, where's the dinosaur dig? I saw the dinosaur, and it's like, there are no dinosaurs. There's nothing to do with dinosaurs. Okay, let's talk about putting Washington together now that we realize that these pieces are coming from the ocean, and then we can look at the evidence finally to try to build a case for Mexico moving north. So you've heard of something called Pangea, I'm guessing. It was a supercontinent where all the continents of the world used to fit together. And those continents were together between 300 and 200 million years ago. So this is before Baja BC. And you'll notice that Spokane was the west coast of North America at that time. So there was no Washington at all, Mexico or not. There was no Washington during this latest supercontinent. So how are we going to build this state piece by piece? Well, we're going to start marching closer and closer to today, and we're going to have these scraps of things out in the oceans start coming in and adding to the edge of North America as we drift North America away from Africa. These are all very accurate maps, carefully constructed. Here's this old shoreline of the original Pangea through Washington. So there's debate about where this old shoreline is exactly because it's buried in a bunch of lava. But you could pick Ritzville if you wanted. I mentioned Spokane, but more technically maybe Ritzville's the spot. But again, the actual boundary is beneath all this lava. Let's look at that again. Here's North America splitting away from Africa. And as we do that, we're going to start adding pieces of ocean rock, like I was just talking about. San Juans, the Tianaway, etc. All those green rocks are coming in, piece after piece. Now this is ignoring the Mexico story. This is just simply bringing stuff in. We're going to get extra ambitious before we quit. By the way, it's a beautiful day, and you just kind of walked in here, and it seems a little bit intense, doesn't it? I just wanted a couple of nice pictures of Mount Stuart, maybe a story or two, and I would have been fine. So I apologize if this is a bit too much. I mean, look at that map. Look at these maps. Look at how complicated these maps are. These are all of these things called exotic terranes. This is all of British Columbia, all of California. These are all the oceanic scraps that came in. It's a mess to try to sort out a particular story. Another map showing the same thing. Mexico, California, Oregon, Washington, British Columbia, all of Alaska is made out of these scraps of things that came in from the water. But there are specific dates where much of the material came in. 150 million years ago, a bunch of the stuff came in together. 100 million years ago, a bunch of the stuff came in together. Let's not get hung up on that. Let's not get hung up on that. Again, I just want to show you how beautiful and daunting these maps are. This is Seattle. This is driving from Seattle up through BC up to Alaska, Anchorage. And every one of these colors is a separate scrap of land that was added. So there's going to be many, many decades of work to continue to try to put this story together. But what I'm trying to do is do the 1-2 punch. We can think of it that way, a 1-2 punch. The first punch is bringing all this material in and adding it to North America someplace. The second punch is shifting a bunch of it north. And what I mean by someplace is the most convenient way to understand this map is just to have this stuff come in at the latitude it's in today. What we're really doing with the ambitious part is realizing that most of this stuff was added much further south and then was shifted north. By the way, just to complicate things even more, this is the eastern part of North America. And there's an older exotic terrain story there. There's not a Mexico thing there, but there's an old exotic terrain story there. These were terrains that were added to the east coast of North America before Pangea was assembled. Just in case your mind isn't expanded enough tonight. Okay, let's finish out with the concept of bringing things in. I think we're overwhelmed maybe by some of this, so let's just blow past. And finally, let's look at the evidence that got me excited more recently to finally try to address this. You remember in the introduction, Jack Powell saying Mount Stuart so controversial? And I introduced the concept of Baja, BC, which is moving what? 2,000 miles between 75 and 45 million years ago. Well, even in geology circles, that was not an accepted thing. And if I could use myself, I wasn't a believer in Baja, BC until recently. And that's because the main evidence for Baja, BC was one line of evidence, which I'll share with you in just a second. And the main point is, this big national meeting I went to, it happens around the country every year. It happened to be in Seattle this past fall. They had a whole session with all of the leading geologists working on this. Looks like nobody's there, but it was a huge ballroom. I was just sitting in front. And just one talk after another with all this mind-blowing new evidence to support Baja, BC. And this was October, and I had both knees replaced, both this fall and winter, so I had a lot of time to read. And I just started emailing these guys and say, could I get your papers? Could I do some reading? Can I email you some questions? And I basically fought my way through all of this new work, basically the last 30 years of work, to try to put a story together. So, cows, glacial moraine, Thorpe gravels, and Mexico. So, what is Mount Stuart? Mount Stuart is granite. Where does granite form? Granite forms underground when you have a big blob of magma that you slowly cool in the dark. Most commonly, that forms underneath some sort of volcanic system. So the granite of Mount Stuart is 93 million years old, and we're simply saying, and this is not controversial either, maybe I should probably do this lecture sometime and just have a big, scoreboard or something. And every statement I'll, controversial or not controversial, it's hard to keep all this straight. All sounds like baloney after a while, maybe. So this granite is formed underground in a magma chamber, and in the case of Mount Stuart, there was a 93 million year old volcano that had magma that cooled underneath it. That's Mount Stuart. So where did the original idea of Baja, BC come from? Why was Mount Stuart the centerpiece of the discussion? Well, let me go back. So the answer is a guy from Western, ironically, Merle Beck. He's still living. I just got an email from him today. Started this whole Baja, BC thing in the early 1970s. He had some grad students at Western. They came to Stuart, and they sampled Mount Stuart. What that means is they had a little rock core, So it's like almost like a power saw, you know, one of those. But they can drill a wine cork-like hole into the granite and basically extract granite from the mountain. And their sample is truly a wine cork-like sample. But before they pull the wine cork out of the mountain, they carefully measure the orientation of that rock. And specifically what they're doing is they're carefully measuring magnetite grains in the granite. So granite is made out of minerals like quartz and feldspar and biotite, but there's a tiny mineral called magnetite. And it's called magnetite because it's a mineral that aligns itself with the Earth's magnetic field as the magma is solidifying. And so this guy Merle Beck says, we've been studying the magnetite grains in Mount Stuart, and they are funky. Because you can look at the orientation of those magnetite grains and say something about where on planet Earth that magma solidified. In other words, you can try to say something about the old latitude of the granite. Well, hardly anybody in geology knew anything about paleomagnetism. Certainly hardly anybody in geology did the work. So this guy, for much of his academic career, from the 1970s onward, was saying, according to the paleomagnetic evidence of the granite of Mount Stuart, that granite formed down in Mexico. And as a new graduate student in Idaho, I remember we read that paper, we were all kind of joking about it, like this is baloney, you know. Because nobody understood the details and it was hard to take the guy seriously. So my point is, for the last, from 1970 to the year 2000, Baja, BC was not really accepted by many people because the only evidence for this Mexico transport was simply the paleomagnetic evidence, which even the geologists, for the most part, had a hard time understanding. But maps like this started showing up. What I just tried to do on the whiteboard. Here's our block down in Mexico. Here's our block heading north. Here's our block ending up in the trailing edge of that block is the North Cascades, including Mount Stuart. Transport between 75 and 45 million years ago. So I wouldn't be giving this talk to you if I hadn't have gone to that session last fall. Because what do I have? I have more than paleomagnetic evidence. Now here's me around Christmas time going stir crazy with my recuperation. And this red dot is Mount Stuart, and here's the green dot, the San Juans. And I just wanted to use some colored markers and try to follow these guys as they're heading north and getting to their present location. And by the way, there's also geology of today's Baja, Mexico, and today's Mojave Desert, etc., that are part of this story. Now, if you're hung up on the northern transport and not seeing how that's possible, here's my attempt to address that. For many millions of years, we had an oceanic plate that was moving towards North America. It was called the Farallon Plate, a big ocean plate. Today, we don't have the Farallon Plate. We have a different plate called the Pacific Plate, which is basically moving towards Japan. But back then, we had a different plate coming at us. During this Farallon Plate time, that's why we had all this material coming and adding to the edge of North America. But here's the key. Between Farallon time and Pacific time, there was a northward moving plate called the Kula Plate. And guess when the Kula Plate was active along our west coast? Between 75 and 45 million years ago. In other words, the existence of the Kula Plate almost seems convenient if you're pushing this, but there's a lot of good evidence for this plate. When we had the Kula Plate moving north, that's when we have our Mexico to British Columbia transport. And that's why we no longer have that motion heading north. So what finally is the new evidence? My God, what time is it? It's 6:45? I've been waiting 45 minutes, you say, for the evidence this guy's finally going to give me? Yes. So I want to show the new evidence that I got excited about. Plant fossils, bedrock matches, and a new mineral called zircon. I'm almost done, in case you're getting fatigued here. But this is the guts of the new evidence. So there's been work done in the last 10 years to look at fossils of leaves. Some of you know that just north of town, you can look up by Blewett Pass and you can find beautiful leaves that are fossilized. Well, these are much older leaves that are up by Winthrop, Washington. Not really Republic. I know that's a leaf area too, but this are slightly older rocks of the Winthrop Formation, 100 million years. And I'm no expert, but there are people who are experts in studying the shapes of these fossil leaves that are 100 million years old, and working with the shapes of the leaves and saying something about the climate, saying something about where those trees were living. And yes, there's lots of information about global climate change, and even going back that far, but if you factor out all of that, it's still a puzzle for some of these leaf shapes at our latitude. And the basic message from this work is that those leaves of the Winthrop area, 100 million years old, were from trees that were living at 38 degrees north, which is 1,300 miles south of their present location. Now, if you're trying to convince somebody of this crazy Baja BC story, and all you've got is this slide, nobody should listen to what you're saying. If you want to say something truly profound, and especially against the grain, you better have many different kinds of evidence that are all pointing to the same conclusion. You've heard of maybe a guy named Alfred Wegener who was trying to convince the world that this Pangea thing existed. And he needed many different kinds of evidence that were all agreeing before people bought his idea. This is something similar. To say Mexico is moving to British Columbia needs multiple lines of evidence. The paleomag by itself didn't work. This by itself is not going to work. So there better be more slides here if I'm going to try to convince you. And I think there are a few more. Maybe this is the most visceral way, the most tangible way to try to convince you that long-distance transport has happened. Wenatchee, Washington, US 2, crossing the Columbia River. Got your bearings? Cle Elum's up off the slide here, right? So when you drive from Wenatchee to land, you got two options, right? You can be on 97 on the east side of the river or 97A on the west side. Let's go 97A on the west side. And what does that look like? Well, you know, your kids are in the car, like, are we there yet? No, we got another half an hour. Okay. So there are some rocks. You didn't have to come to a lecture to learn that there are rocks, thanks to the highway. There are rocks on both sides of this drive, just north of Wenatchee. And this is metamorphic gneiss. It's not green, like we were looking at before. There's a bunch of kind of, I don't know if they're super photogenic or not, but they're complicated metamorphic gneisses and schists. And they're distinctive. Their look is distinctive, their minerals are distinctive, their isotopic chemistry signature is distinctive, and that's important. I'm building up for something right now. I don't know if I'll get the reaction I'm looking for, but I'm going to try anyway. So just north of Wenatchee, Washington, on 97A is something called the Swakane gneiss. Very distinctive. There's only one other place in the American West that we can find that distinctive rock. It's in Palm Springs, California. Same rocks, same age, same isotopes, same folds, on and on and on. They're twins. And you go, well, okay, well, what are the odds, you know? But then you start thinking about it, and you go, okay, well, maybe this and the rock of Wenatchee used to be, like, together. And then they got broken by this fault, sending the Wenatchee rocks north. And then you're like, well, wait, this isn't Mexico. I thought you said stuff was coming from Mexico. Well, even this rock has moved north. So what I'm trying to say is, backwards, this rock and this rock were both together in Mexico once upon a time, 70 million years ago. And some of the rock made it to Palm Springs, and the other rock made it to Wenatchee, Washington. Baja, BC. So I think we got to change this. So we're circling rocks that are identical between the North Cascades of Washington and the Mojave Desert of Southern California, realizing that both of these were originally in Mexico. I need more, though. I need more evidence to try to convince you that something's going on. And remember, you don't have to buy this hook, line, and sinker, because if we had 1,000 geologists from across the country in this room, I think maybe 40 of them would be with us, and 60 would be not finding problems with this. So I'm confident that eventually this will be an accepted story. So you're getting kind of a cutting-edge, breaking news kind of a thing here. I may be wrong. This may be baloney, but I'm excited about the potential here. Can you read this? This is Joshua Tree National Park. So again, we're now down in Southern California. We're also near Palm Springs. This is a geologic map, so these pink areas are granites. 93 million years old. Joshua trees, we don't care about it. Granite, tonight, we care about it. The granite of Joshua Tree is part of a larger batholith called the Peninsular Batholith. This rock is 93 million years old, and it has a paleomagnetic signature. Remember those magnetic grains that have a particular reading. And again, this stuff came from Mexico. It's now in Palm Springs, but it was 1,000 miles further south. Can we find a bedrock match? Can we find a twin that was part of this granite block that is no longer in Southern California? Where do you think we're going to go? We're going to go right here. So the rock of Mount Stuart and the rock of Joshua Tree National Park outside of Palm Springs, same rock. Same age, same paleomagnetic signature, and they both were originally magma that cooled in Mexico. Those blobs of magma were formed when an ocean crust was subducting and feeding these systems. But that's not really the juicy, sexy stuff we're doing tonight. The juicy, sexy stuff is breaking off a portion of Mexico and sending it to the north. And that's what I've been trying to do with you. I gotta have more, though. I gotta have more. There are matches with fossils. So these are ammonites, sea creatures. These are photos from the Burke Museum over in University of Washington. And they are of the particular age that are going to help us here. These are in rocks. These fossils were found in rocks that were part of the Mexico transport. So here's what those ammonites looked like when they were alive in the ocean water. Again, here's what these fossilized ammonites look like. So there's a guy named Peter Ward who's written a lot of popular science books, and he works at the University of Washington. And he's an ammonite expert, and he's fond of a particular ammonite that has only been found in a couple of places in western North America. You know what we're doing. We're doing the same thing again, right? So in this case, he's got a collecting site on Vancouver Island. We're now in British Columbia. There's a little town called Nanaimo, and then just north of that, I've never been here, maybe you have, Denman Island and Hornby Island. We're basically on the east coast of Vancouver Island. And in those sedimentary rocks are these very rare ammonites, 77 million years old. Not found very many places. Where do you think we're going to try to look and find more? South of Ensenada, in Mexico, on the Baja coast, are same ammonites. Distinctive look, distinctive age, distinctive rock. It's the same stuff. So these are the guys that stayed home in Mexico. The guys that left and moved 2,000 miles to the north are now in British Columbia. Baja, BC. I got one more piece of evidence for you. Let's do that. I got one more piece of evidence, and it's going to be up to me to try to teach this with the right words. It's not an easy concept. So it's not a good move as a teacher to finish a lecture with the most challenging thing to try to talk, but we'll maybe try it. No, we will try it. Okay. It's a mineral called zircon. So the mineral that was up, so this says paleomagnetism, so I'm reviewing now our evidence. We had paleomagnetism, which just a few people bought, and the mineral there was the magnetite minerals in the granite. Then we looked at the plant-shaped stuff. I don't know if you bought that or not. Then we just looked at a bunch of bedrock matches. Remember? Wenatchee and Palm Springs. Mount Stuart and Palm Springs, granite. And then we just looked at the ammonites, Vancouver Island and Baja, California. We're finishing with a very tiny mineral called zircon. So these minerals are in a lot of rocks, this mineral called zircon. You haven't heard about it because they're tiny and not very valuable. But they're valuable academically because they're extremely durable. These little zircons do not crumble. They don't break down. They don't alter. And we're looking at high-powered microscopes now. These are micrometers, microns and millimicrons, looking at the details of these zircons. Each of these little zircons is the size of a grain of kosher salt, a coarse salt grain. So these are not actual zircons, they're actual salt. But that's the size we're talking about. And this is the exciting new, the latest in this round of new evidence that have people excited. Studying zircons. Okay, can I do this? How am I going to do this? How am I going to talk about this? Let's see if I can do this. Here we go. So, remember the whiteboard right at the start? We're taking a block of crust down here, remember my rectangle? And we're going to move it north. Let me test you. Mexico to British Columbia. What's the distance again? How many miles? Thank you. And harder question, when are we going to start this movement? How many millions of years ago?
75.
Beautiful, 75. And by when are we going to get this thing in place up here? 45. 75 to 45. Beautiful. Thank you. Now, here's the concept. Where's the block of crust now? It's up here. If you go to the surface of that block, there are a bunch of zircon crystals that are Precambrian in age. Precambrian means like 800 million or 1,000 million, in other words, a billion, or 1.2 or 1.4 billion years old. So let's just bite that one off and think about it for a second. On top of these terranes, we're finding super old zircons, much older than this whole transport story. Okay, that's weird. How'd they get there? Here's the concept. When our block of crust was down in Mexico, there were zircons that were eroded out of the oldest parts of North America. These are numbers, you probably can't read them even in the front. This is 1.7 billion years, 1.7 billion years, 1.4 billion. This is the oldest part of North America. And there are zircons that were eroded out of this old part of North America, and rivers transported those little salt grains, those little zircon grains, from the old part of North America and carefully placed those salt crystals on top of our Baja, BC block. I'm going to say this again because this is important, and we're finishing with a bang. Here it is again. Precambrian zircons were eroded away, transported, and redeposited on top of our Mexican crust. Okay. Now what are we going to do? 75 to 45, we're going to do our moving. We're going to cross the border. Ha ha ha. Go all the way up. But what's taking a ride with our block? These zircons that are originally from old North America. So the excitement is, oh man, we got these super old zircons. Can I figure out where those super old zircons came from? Did they come from this part of old North America? Or did they come from this part of old North America? And if the answer is B, they came from this part of old North America, we got to get this crust all the way down here to get those rivers to do our transport story. That was my attempt to talk about detrital zircons. I'm going to go back and try it one more time. I was talking about detrital zircons, which means those teeny tiny minerals. Detrital means they're moved by rivers. We erode the zircons out, they don't crumble away, and we redeposit them in sedimentary rock. And so I'm going to go through those slides one more time. Each of these guys is a little salt crystal, not really salt though, it's zircon. And we're analyzing the rims and the chemistry and the ages. In other words, we're getting a whole chemistry fingerprint on that zircon and then ultimately trying to tie it to its source. So these are plots that we don't need to get into, but there's been tons and tons of studies on these different zircon populations in different locations with different chemistries. And it's a detective game to try to figure out where those very old zircons came from. And it's really a debatable topic right now. The group that I'm fond of are convinced that the zircons are coming from the Mojave. There's another group that say, no, Baja, BC is total bullshit. And those Precambrian zircons came from northern Idaho. And we don't need 2,000 miles of motion. We've got old Precambrian rock in Idaho. We don't need 2,000 miles of motion. And so there's debate between these zircon expert groups right now that will eventually be solved, but we're not there yet with the story. So if we take all that evidence, here's our block, our Baja BC block in Mexico. It's in California, it's in Oregon, and it's in Washington, British Columbia, where it belongs. Here in God's country. So, is Mount Stuart granite? Yes. Is it granite from Mexico? You've heard my case. Is Long's Pass or Ingalls Pass or Earl Peak serpentinite from the ocean? Yes. Was it added to Washington or was it added to Mexico? You've heard my case. Mexico, Mexico, wife, son. Thanks, everybody. Coming tonight. If you've got questions, just come on up here in the front. We'll have a little mini session here before we kick off. Thanks again. You have a good night now.